The answer to that is be glad that I do it. It's enough work already, to tell you honestly. When I first started doing it, I actually put little descriptions in there, and now I'm just happy I get them up there. So, yeah. Sorry, buddy. So you'll be right. So first thing I want to do, any questions from any homework that we might have possibly looked at already? Oh, good. Were you here the first day?
No, oh yeah.
Oh, that's the answer. Yeah. Did I miss a few?
Yeah.
Sorry. I see the answers for that. So any questions on the homework yet? You guys are all like, dude, not done the homework yet. Okay. Or there's no questions. I could be optimistic about it. And we really kind of just barely got into 11.1. I hope so far it's pretty simple. I mean, the vectors are possibly something new. If you've had physics before, they're definitely nothing new. You have been vectored out like crazy if you've had physics. So you're going to have a great time actually for the first few sections because it's going to be all news to you. But it's really not that difficult to get, is my hope. So a couple things I kind of didn't cover yet in section 11.1. Let's go ahead and try to close that thing out. When you have a vector, and the book and I both start with vectors just kind of hanging out there. There's no frame of reference, right? What do we normally use as a frame of reference for something like this?
The origin.
Yeah, well, the origin, meaning that there's some kind of coordinates axes set up. It could be rectangular, it could be who knows what. But when we start off with just vectors hanging out in space, and we start talking about, well, how do you add them and stuff like that. But what I want to bring it down to is how do they relate then to the coordinate axes? How do they relate to points that we're used to dealing with before? And I sort of gave us a little preview of this last time. I asked you kind of a question a little prematurely, just to get you guys started thinking about it. If I have 2 points, let's say I have a point here, and I have a point right there. So this is the point P, the point Q. This is -4, -1. This is 2, 3. What is the vector? Just let me turn it on its head a little bit. QP. The name of a vector is the point that that vector would point to if it started at the origin.
-6, -4. Is that a 6 or a 2?
That's a 2. Yeah. 2, 3. Exactly. I mean, how do you tell? If you did move that, you got to move this guy here, right? So thankfully, you don't have to redraw it or anything silly. You just do the math. We're used to this kind of math. This is the kind of math that you have to do for distance formula, all that kind of business, right? If you did move this over 2, that would make this go over 2, so now this would be -6. So what's the real math behind here to find QP vector? What you would do is you would take Q, you would take the P minus Q, right? Basically, the components of P minus the components of Q. The math there is pretty simple. So like you said, this would be -4 minus 2, and then -1 minus 3, -6, -4. So there's a point that I want to make, and I really don't want to make too big of a deal out of it because it really doesn't affect things. Where I put the origin, did I have to put it there? The point is some point in space. It's kind of set, right? If I have a star in space, there it is. Whatever I do over here, I'm not going to, the star moves, the star's following me. No. What I can do is I can change my frame of reference, right? So it really, what's arbitrary here is where I put my grid lines. So the name of the vector is the point it would point to if that was the origin. Everybody with me? The math is not really affected. You know, you got to worry about if you have a plane going, then obviously its velocity vector is kind of coming off its nose. Does it really matter if you kind of move it? No, it still has a velocity. I don't have to say starting at its nose or something silly, right? Okay, cool. So that by itself. In fact, throughout the whole semester, when I have the vectors, pretty much on a test, I'm going to have, here are some points. Now, come up with the vectors, QP, PR, ST, and then do all this stuff with the vectors you just found. So you really don't want to subtract incorrectly, because then the whole damn thing's wrong. Right? Don't freak out. I normally give partial credit. If you make a mistake on part A, I'm not going to kill you B through J. That would suck. Right? So thankfully I give you partial credit. Okay. So far, hopefully this is nothing major. Oh, there. Cool. When I say the word scalar, what does that mean? Well, it could be a multiplier, but what's scalar by itself? Okay, sort of. True, meaning it's a real number, right? So a vector is sort of a ray in a way, right? So geometrically, it's got some 2 components to it, or 3 or 4, depending on how many dimensions we live in. A scalar is always going to be just a real number. It's not going to denote a vector. It's not going to have any direction associated with it. It's just a real number. So when I say scalar multiplication, that's really just taking, if I have a velocity vector for my car, and if I want to scalar multiply, I step on the gas, right? Because then what happens to my velocity vector? It gets longer. Or I hit the brake, and then it gets smaller, right? You guys with me? Cool. And if it was acceleration, it'd point backwards. But whoa. So scalar multiplication, I can't remember now off the top of my head if I talked much about this already. That's the first very basic operation we can do with vectors. And that's really just to make them longer, make them shorter, make them point in the opposite direction if I use a negative scalar, right? Use a negative number. So if I have a vector -6, -4, and they ask you, okay, what's 3 that? That's an awesome question. That would be
-18, -12.
right? Can somebody kind of explain to me, or can you think about this for a second? Let me ask you this question: how would you figure out the length of this, the magnitude of this vector?
Pythagorean theorem.
Pythagorean theorem, right? Because it's really related to the distance formula. So it'd be the square root of. And let me make sure I'm not going too far here. When I write a vector like this, where is its tail? I mean, not the tail, but the beginning where's the tail, yeah, the head's out somewhere, but the tail is at the origin. So when I do my distance formula, it's going to be -6 minus 0. So really it's just this squared plus this squared in there, right? That's awesome. That's how you find the magnitude of a vector. You just square these guys, add them up, take the square root. That's the distance formula exactly. So I get 36 plus 16, square root of 52. Which you can reduce, and it's amazing, whatever. Right. So if you did the magnitude of this, it would of course be 3 times as big as that. In fact, inside of B, square root of 9 times 52, that would be 3 times as big, right? Hopefully you guys could see the math of that. When I put square root of -18 squared plus -12 squared, and this is where I was a little bit, well, only a few people. Be really careful about things like, can I do this? No. Okay, please, dear God. Don't make me cry. When you're at Math 281, I expect to only see errors like that every now and again. We are human. So, every now and again we'll do something like that and we're like, oh shit, of course I know that's not true. I understand that. If I see that a lot, it's going to make me cry. You want me to cry. You want to be happy when I'm grading your stuff. So desperately don't make. We are all human. If you make this mistake sometimes, I'll make this stupid mistake sometimes. I know I will somewhere. I'll make something like that on that level. Don't do that all the time. It makes me scared. How the hell did you get here? Here, you'll notice that out of both of these comes 9, right? 9 comes out of here. It's negative 18 squared. So you actually got 3 and 3, which would leave 9 times negative 6 squared plus 9 times negative 4 squared. So I'll pop sure 3. So it's 3 times as big. So the math is not that big of a deal. You guys with me here? So thankfully, what I'm trying to say is this. Exactly what you hope would happen. 3 times a vector should end up being something that's 3 times as long as the original vector was. And of course it does. And hopefully on the way you guys are picking up some of this math, how this works. Something I'll be doing a lot is finding the magnitude of a vector, the direction that it points in, those kind of things. Okay. Don't worry, by the way. If I'm you, I might be worried. I was worried the first day because I was actually losing my voice, but I'm like, God, I speak way too much. But I have some handouts, so you guys are going to work together on some stuff. I'm not going to just purely lecture the whole time. Thank God. Right. I get a little tired of my voice. Oh, so here's the cool thing. If I have 2 vectors, I'm trying to make this just messy. Now, adding these visually gets a little interesting. You can't be quite as precise. You have to kind of make a nice graph, kind of see what point it ends up at, and all this kind of business. Adding these based on components is easy as hell. It's exactly what you hope would happen. What do you hope would happen for u plus v?
The x's.
Just add the x pieces and add the y pieces, of course, right? And thank God that's exactly how it works. And of course it only makes sense if you think about it. If I add up the x pieces of something, so if I have to go 3 blocks over and 4 blocks up, well, it's the same as 1 block over and 2 blocks up, and then 2 blocks over and there are other 2 blocks. I mean, I can break the components down and I end up in the same place. So I should be able to add these things component-wise, right? How are you guys doing so far? Okay, so I'm kind of hoping to not have to get too deep into a proof. I mean, this is something that kind of makes sense. I should be able to do this. So sure enough, u plus v would be -2, 3. Okay, sweet. All right. If you think about it, this guy would point 1, -4, roughly, and this guy would be -3, 7. Right? So that's where they are. That's their position. That's their standard position when they're pointing away from the origin. So if I do pick this up and put this guy here, it does make sense that they end up, well, I'm hoping they make sense. 1, -4, yep. -3, oh, I didn't go far enough back. -3, 7. So if I pick this guy up and put him here, there we go. Pick this guy up and put him here. It kind of makes sense to be -2, 3 if I just had the right. I made this guy way too short. But you guys can still see if you drew it out, you can see it kind of makes sense. Whatever this guy does, in this case, he's undoing this piece. He's going backwards, right? So I like the idea of this, trying to get from one house to the other. That's how you first describe coordinate axis in the first place. I got to go 5 blocks up and 4 blocks over to get somewhere. So that idea still holds, right? Go 1 block up, oh crap, go 3 blocks back. Well, it's effectively 2 blocks back. No big deal. Okay. So here's something I want you guys to think about. I think I'm ready for this. Yes, cool, perfect. Here's where things get a little more interesting. If given a vector, let's say I have a vector 2, let's make it a little less crazy. 3, -4. I wish you guys are out there saying, why is that less crazy? What do you think a unit vector is? Unit, of course, meaning what? Now be careful, somebody's getting a little heavy. There are certain standard unit vectors that we have already. What's true about those unit vectors?
It's a vector in the direction that has a magnitude of 1.
Okay, so the direction doesn't really matter. A unit vector is any vector that has a magnitude of 1. And it kind of makes sense because remember the good old unit circle had a radius of 1, so that's kind of like where it comes from, obviously. Unit meaning 1. So is this a unit vector? Just by looking at the damn thing, you know it's not a unit vector, right? How could I make this? How could I find the unit vector that points in this direction? Now when I say that, hopefully you guys have picked up. The minute I write down a vector, what does it tell you? A direction and a length. Very quickly, there. I have defined a direction and a length, but let's say, no, I just want a unit vector. I don't want something that's strong. I want something weaker, just a length of 1. Yeah?
You put it into the R theta polar coordinates?
No, I don't do that. That's all right. No, it's not a bad idea, but it will eventually work, but it's going to be a little too long. There's actually a more direct way to do it. Beautiful, right? Obviously, this guy has some length to him already. So if I just divide him by that length, how long will that resultant vector be? 1. Sweet. So the unit vector in the u direction. So one thing, I've got to be really careful because a lot of this is kind of new to you guys. Whereas if you do a lot of math, this is really the building blocks right now. This is the building blocks of a lot of what comes after this. And of course, not just math, engineering, physics, all these other things. So I got to be careful about remembering that this is new to you guys. Because this is very, I'm hoping you guys are picking up some of this terminology. Whenever I put a vector down, I am defining a direction, right? So I can talk about things in certain directions by identifying vectors that kind of lie in that direction. Cool, okay? So to find this would be the vector itself divided by its length. This might make sense to some of you guys. It's almost like standardizing the vector, right? You divide by the length to kind of norm it, to kind of make it a length of 1. It makes it into sort of a building block. If I have something that's length 1, I can build off of that very easily. Because what do I do to make it 3? I just put 3 of them down. If I had something length square root of 2, well, that thing sucks major. All right, guys, here's a square root of 2 length board. Now I need a 4. Screw you. Give me a 1 length board. Let me put 4 of them down. There's your 4. Go away, right? So it's kind of a nice way to make a building block. So in this case, what's the magnitude of u? 5. Beautiful. Some of you notice hopefully a 3, 4, 5 triangle, right? So look for those. It's not going to happen a lot, but sometimes they happen. So the magnitude, if you want to look at the work, 9 plus 16, square root of 25 is 5. So then the unit vector would be 3, negative 4 divided by 5. Which really, the book kind of goes both ways with this, but I personally like to write it as a vector at the end, not a problem. Right now, this is a problem. This is scalar multiplying a vector. Write the answer for me, right? So the answer would be 3/5, negative 4/5. So that's the vector that does what?
Points in the direction.
Points in the direction of u, magnitude of 1. I love it. Sweet. How are you doing so far? This is really nothing major yet, right? Oh, on page 687. If you have your book with you, page 687. Here's what I was hinting about on that first day. And remind me, how many guys are math majors? Okay, just a few of you guys. When you get further along in mathematics, you'll start to realize why associativity and commutativity. If you talk to a algebra student, they're like, those things suck. I can never escape them. They always come up. But when you go further in math, you realize, well, you can create whole sets of numbers that don't have the commutative property. If you've done matrices, you know that they don't have commutativity of multiplication. If you don't have the matrices, then you don't know what the hell. But you just can't. A times B is not equal to B times A necessarily for matrices. So that's where it starts, you're like, well, that's interesting shit. So far it's been like, this property and this property, and now it's like, this property don't work. Here, like I was saying earlier, a lot of vectors, the vectors inherit most properties of real numbers that we're used to. They inherit commutative property, they inherit associative property, so forth. And of course it only makes sense because when I add two vectors, it really ends up adding several real numbers. So they should have the same stupid properties as real numbers. Okay. How are we doing so far? So far, so good. Okay. When we get to multiplication, we might not inherit all of these properties, but we'll get there. Cool. Oh, real quick word about the zero vector. What do you think should be true about the zero vector? First obvious thing is
No length.
the length is zero. That kind of makes sense. So what does that mean about the other property of vectors?
No direction.
The funny thing is, and which happens a lot with zero, you could either think of it as having no direction or having all directions. There used to be, I remember a long time ago, there was a billboard out, I'm sure this still exists somewhere, but in Virginia, I could drive and it'd tell you, the wind 3 miles out of the west, 6 miles an hour out of the southeast. And then you drive by every now and again and say 0 miles out of the northeast. And you're like, wait a minute, how's it going 0 miles per hour out of the northeast? And of course, because it was just coming out of the northeast and it just gets stuck there, right? So the zero vector, the book says officially it has no direction. In reality, it really could be either way to look at it. Either it has no direction or it has all direction. Because it really doesn't matter. Oh. I wanted to show you a very simple proof. Just to kind of show you what proofs might look like. For some crazy reason, maybe you'll have proofs to do eventually. Proof of, I think this is property, the last property, proof of number 10 property. And this one is the one that talks about commutativity of scalar multiplication. Now, let me just get a suggestion maybe. How would I go about proving this? I mean, seems pretty obvious, and you could possibly argue it using words, not really using much mathematics. If I wanted to do a purely mathematical proof, where do you think I should start? Because how do they define scalar multiplication? What is this defined to be in the first place? How do you really break this down?
A multiple of a vector.
What is V?
Vector.
So what would it look like here? Yeah. So what we do in general is you call it V1, V2. And then you can bring it in. You can show what really happens. I can't show what really happens here. How do I bring the C in? Do I put it right there? The C's in there. No, I can't do that. Here I can bring it in and show you what really happens. If I could write, then that'd be great. So I do the same thing here. So we've already done this piece here. And this should sound familiar. How do you prove, like trigonometry? One way you can do it is to work with both sides and show that they end up in the same place. That's exactly what we can do here, right?
Mm-hmm.
So here it would be A times that thing, right? Because that's what we just figured out CV is. And of course, what's the scalar multiplication tell you can do here?
ACV1.
Yeah, that comes in. It would be ACV1.
ACV2.
Which, by observation, is what this would be. This would be V1, and then you bring the AC, multiply it in, V2, and you multiply it by AC. Therefore, I have proven that property. Using the definition of scalar multiplication, I've proven this further property. How are we doing? Okay, some of you are completely bored, I understand. So, just to warn you, it's obviously somehow a bit of a warning. I do like putting proof problems on tests. And they will, the first few proof problems could use rewriting the vectors out into full component form. And then you can attack them. Right? The last little thing of 11.1, and then I'm going to give you guys a handout to kind of work on. the last little thing out of section 11.1. In this case, we'll use let's use a force vector since we can visualize that. So again, those of you who've had physics, you are at an advantage over those who haven't, because it focuses so much on vectors. Which for those of you who haven't had physics tells you why the hell we do it here, because you're going to do it, it's useful in other places. If I have, here's your very basic problem in physics. If I have a crate and I have a rope attached, right? So those of you who are in physics or used to have physics, you are like, holy crap, that sounds very familiar. And I'm pulling it at an angle because I don't want to go like this, and if I just pull it straight up, it's not going to go anywhere. So I'm pulling it at a comfortable angle. And I'm trying to move it, obviously, this way. What will the components be? Let me see how I want to set this up. There it is, cool. So let's say my force is 20. On the newtons, we'll just go ahead and use the right units. 20 newtons. And it's an angle of 30 degrees with the horizontal. Which, of course, seems to be an important angle because the only way to not waste any of my force, neglecting friction, so somehow we got that beautiful frictionless surface. The only way to not waste any force really is to have it being pulled forward. So you guys realize the minute you bring friction in, why does it make sense to have a bit of an angle to it? Because then some of the force goes into alleviating some of the normal force, which is what makes friction happen. If you can pull something off the ground a little bit, then it'll move easier, not as much friction. All that aside, how do I find the components? How do I define this thing? How do I come up with what this vector is? I want to know what that vector is there.
Magnitude times sine 30 degrees.
I like it. And here's where, if you remember your cosine likes x, sine likes y, this kind of thing is stupid easy, right? To find the x piece of this, how would you find the x piece of the force?
20 times cosine 30.
20 cosine 30, because x likes cosine. And what is the cosine of 30 degrees? Root 3 over 2? Yeah. Cool. So that'll be 10 root 3 at the end of the day, right? The 2 and the 20 make 10. And Fy would be the other piece. So 1/2 of 20, 10. So it'll be 10 root 3, 10. Cool. So what's the magnitude of this vector? 20. Yeah, it's just the reverse of what we just did, right? So make sure you guys saw that. It was an easy question, guys. Okay, so let me do this. Let me go ahead and give you guys. This is a two-sided deal. We just did 11.1. On the back is 11.2. So maybe don't try any of these yet. So 11.1, go ahead and try these out. You guys can work together, and then we'll talk about the answers. We'll take a break, and then we'll do 11.2.
Drop kick and won't break it.
Oh yeah, go ahead. Anytime you need that, you don't have to wait for a break for that. I won't take it personal. you're starting this, I want you to realize the pretest we did. Chapter 11 is sort of, it's going to have its own difficulties pretty soon, but it gives you a little bit of time to go back and review some of that calculus stuff, the trig stuff, the integral stuff, the methods of integration, all that kind of stuff, before we hit integration of vectors and so forth, and line integrals and surface integrals and all this stuff. If you don't remember the basic integral methods, ain't no way you're going to be able to do this other integration stuff. All right, so you got some time to review the stuff that was on the pretest. This chapter 11 is kind of new stuff, not hard stuff. You got a little bit of time to review at the same time.